Hi, my name is Gabe Mungeb, and here is my Lab 2 for Physics 2211. In this lab, I analyzed projectile motion of a tossed paper ball and used Newton's second law to model it with and without air drag, comparing the predictions to my experimental data to estimate the drag coefficient. So here's the introduction to my lab. The purpose of this lab is to record 2D projectile motion of a tossed paper ball, build two models via Newton's second law with gravity only with one model, a force acting on the ball, and the second model being gravity and air drag. Use the tracker data to get initial conditions and compare model versus data on one trajectory plot in Excel, and estimate the drag coefficient B by fitting the drag model to the data. The system of my lab experiment was crumpled A4 paper ball, and the surroundings were earth, air, table, paper, and camera. The result ended up being that both models tracked very closely to the data. However, the drag model gives a small improvement over the gravity model. Here are the models and physical principles I used for my lab experiment. The first one being Newton's first law, which is constant velocity used for the x direction of the projectile, the projectile I threw. Newton's second law was constant acceleration used for the y direction. We can use it as a equals f over m, but in the code we use it as the momentum principle, which is delta p over delta t, which we can further break up into p new equals p old, simple math. So the forces in this lab, are gravity and drag. For this lab, we must assume that the ball is in 2D motion, the ball is treated as a point mass, g is equal to 9.8 meters per second squared, b is constant during the flight, and only gravity and air are the forces that act on the ball. No lift, no nothing else. Model 1 is gravity only, which means F net is constant, which means we can use the kinematics equation, the regular kinematics equation for position and velocity, but model 2 is gravity and drag, so F net is not constant. So we have to update all the values each with delta t, and we have to still use the same velocity kinematics equation, but for position we have to use v new as an estimate of v average. The experimental setup. The experimental consists of tossing a crumpled A4 paper ball in a clear 2D arc across the frame, recording the in-air portion only, using the A4 sheets here, you can see, as the calibration stick, fixed camera level with the table, and tracker setup with the x-axis along the table and the origin right below the release point. And the initial conditions are here. The mass, initial position, initial velocity, and drag coefficient, which we found from fitted data. And here's the experiment again if you want to see it. All right, here's the tracker data I got using the tracker tool on tracker, and here are the graphs I got and the points that I graphed that I got from the tracker thing. So here's the x of t, the tx graph with the linear fit, and you can see the values on here. And here's the ty graph, which you can see the parabolic fit values are here. Here's my code. I use glow script and the momentum principle as explained earlier. And again, the forces, model, gravity, and drag. However, we just used, you can see down here, we just used the non-constant forces for kinematics equations because we're going to use B is equal to 0 to have our quote-unquote constant kinematics, and then B equal to something non-zero, a little greater than that. But it's a very, very small number, which I'll explain later. Here are the outputs we got for the computational model. Simulation 1 is gravity only, which is B equals 0, as I said, and then B equals a very small number, greater than 0 for simulation 2. You see with the visualization, the TX graph, TVX, TY, TVY, and the trajectory, the XY graph. All right, here are the results. So graphing all three graphs on Excel, we can see blue is experimental, simulation 1 is orange, simulation 2 is green. The agreement is that both models match the trajectory very well, as I explained in the couple first slides, but the disagreement is that the simulation 1 orange graph slightly overshoots experimental data, especially past the apex, while the green one actually gets closer and closer to trajectory. We have very, very close alignment here, which makes sense because B would, sorry, I don't skip this slide. B would make, the absence of B would make the projectile fly farther than it should have. Here are the differences, maybe why. Air drag is very small, so here's why. There's maybe three reasons. So it's because of the short flight of the projectile. The speeds are well below terminal velocity, and there's a small surface area, so it can't grab the air as much, you feel me? So the models are very, very close. There are also different other reasons like measurement error with the scale from the A4 sheet, camera parallax, and manual tracking introduces small scatter. I can't click the middle of the ball every single time when I'm tracking it. I try, but I can't. And modeling simplifications, we made a really simple model with constant B, perfect level x-axis, and no other forces acting on it other than gravity and or drag. So while both simulations fit the experimental data well, the gravity-only model slightly overshoots, while the drag model best overlays the data, which is consistent with a small but non-zero air resistance effect. All right, here's some additional questions. So what does terminal velocity mean? Terminal velocity occurs when net force is equal to 0, so speed stops changing. From our velocity versus time graph, we can see that with no drag, the graph changes linearly, so there's obviously no terminal speed. But with drag, the graph would approach negative terminal velocity, but our flight is too short and is too slow to plateau. To measure terminal velocity, we could do a long vertical drop, so there's enough time for our object to reach terminal velocity, or we can use copy filters to make a bigger drag, which it reduces the terminal velocity because you have to get F net equals 0, and that's another way we could do a find terminal velocity. But what if the ball is thrown straight up with the same initial speed? Well, upwards drag adds to gravity going down, so there's a shorter uptime and lower peak, which decreases the total time. On the way down, however, drag opposes motion, which makes it longer a downtime, which is increasing total time. So a decrease and increase, so two opposing factors. But, however, for our small b and small travel time, the reduced height dominates because g doesn't have time to kick in and make drag become a real hindrance, right? So it's not really like negligible. It's honestly negligible. So total time is slightly shorter than the original time. The end.